ಹಲೋ
ಸರ್ ಕೇಳ್ತಾ ಇದೆಯಾ?
ಕೇಳಿಸ್ತಾ ಇದೆ ಸರ್. ಹಲೋ ಪ್ರೊಫೆಸರ್ ನಾಗರಾಜ್ ಸರ್ ಜಾಯ್ನ್ ಆಗಿದ್ದಾರೆ ಸರ್.
ಹೌದಾ?
ನಮಸ್ಕಾರ.
ನಮಸ್ಕಾರ
ನಮಸ್ತೆ
ಸರ್,
ನಾಗರಾಜ್
ಹೇಗಿದ್ದೀರಾ?
ಓಕೆ ಸರ್.
ಥ್ಯಾಂಕ್ಸ್ ಫಾರ್ ಜಾಯ್ನಿಂಗ್ ಸರ್.
ಓಕೆ ಸರ್.
ಐದು ನಿಮಿಷ ಮಾಡೋಣ ಸರ್.
ಆಯ್ತು,
ಸ್ಟಾರ್ಟ್
ಆಯ್ತು.
ಮಾಡೋಣ ಒಂದು 5 ನಿಮಿಷ.
ಅಂದರೆ ಸ್ಟಾರ್ಟ್ ಮಾಡ್ತೀನಿ.
Venkatesh sir,
Yes, sir.
start ಮಾಡೋಣ.
Yes.
Good evening, everybody. Good evening, our resource expert for today, Dr. E. Venkatesh sir, Dr. P. Nagaraju sir, DDPU Bangalore. Welcome, and all the participants who have joined, and some more participants will be joining little while from now. And on Cisco WebEx, some have joined, and on YouTube there will be many participants who will be joining because some of them find difficulty in joining on Cisco WebEx. So we have made a link for YouTube also. Many students will be joining. Welcome to all of you. We have with us eminent academician and former principal of AES National College, Gauri Budnoor, Professor VENKATESH. He'll be delivering a talk on thermodynamics. Before beginning the talk, let me give a brief overview of sir's academic achievements. Dr. G. Venkatesh has done his MSc from Mysore University with specialization in theoretical physics. Later, sir pursued his doctoral degree from Bangalore University, and he carried out research at the very renowned Raman Research Institute in Bangalore. His thesis, title of his thesis was High Pressure Studies of Liquid Crystals. Later, he joined as a lecturer in physics at AES National College, Gauri Budnoor, and subsequently retired as professor and principal of the college. Sir also has worked as director of academics and development at Indian Academy Degree College, Bangalore. He has published many research papers both in national and international journals of repute, and also guided many students for PG and PhD research. And he has attended many national and international seminars and conferences in India and abroad. And further, Dr. G. Venkatesh was also a member of POS Mysore University and POE Bangalore University. He was also on the expert panel of Indian Society for Technical Education. And also he was a member of NAC PE team committee. And Dr. Venkatesh was also academic council member of Bangalore University, and he was the chief coordinator of IAPT examinations. And he is a life member of Indian Association of Physics Teachers, Indian Liquid Crystal Society. He has a very vast experience as a teacher. I'm sure many of the students who will be joining this talk will certainly be benefited by such talk, whether it is a CET exam or NEET or JEE or beyond. Certainly, all of you will be benefited by his talk. Physics is very important, not only from the point of view of your CET or JEE. It will be helpful for your, if somebody is joining PCM in the BSc or even engineering or medicine, wherever you go, physics is a very important component. And sir will be talking on thermodynamics. As you know, thermodynamics is a very important chapter in you. It will help you in further understanding the subject well. With this background, may I request Dr. G. Venkatesh sir to take over and deliver his talk. Over to you, sir, for your talk.
Thank you, Sir Ramesh. Good evening to you all. And I am really thankful to the organizers for providing me this opportunity to speak to you on an important topic, namely thermodynamics. So this is a branch of physics which has not undergone any change in spite of the fact that the other branches of physics have undergone. But basically, thermodynamics deals with the study of the internal energy or the heat energy of a system. Also, it deals with the conversion of heat energy into other forms of energy like mechanical energy, chemical energy, and so on. And see, many stalwarts have worked in the field of thermodynamics. To name a few, we have Rudolf Clausius, Sadi Carnot, Ludwig Boltzmann, Walter Nernst, Max Planck, and others. Even Einstein has a certain role in the development of thermodynamics. And this plays a very important role in other branches of science also, namely chemistry, biology, engineering, and statistical mechanics, and so on. So, the basic laws of thermodynamics cannot be derived. One has to understand that the laws of thermodynamics are based on experience. And based on the experience, these laws are formulated, and therefore, there should not be any question in an examination about derive the first law, derive the second law of thermodynamics like that. It is basically an experience, empirical, but its applications are very important. And coming to the different laws, there are three important laws of thermodynamics, namely the zeroth law, the first law, the second law. Of course, as late as 1950, Walter Nernst introduced another law which is called the third law of thermodynamics, which I am not going to deal in this talk. Now, in thermodynamics, actually what we do is we explain the various phenomena associated with heat and the other forms of energy in terms of certain macroscopic properties. The normal macroscopic properties that are used are the pressure, volume, temperature, internal energy, entropy, and these are the various thermodynamic parameters. And another important factor that you must remember is that these parameters are state functions. State functions mean that these parameters are dependent on the initial and final conditions, final states of the system, and is independent of the path along which we reach the final state of the system from the initial state. So, thermodynamic parameters are pressure, volume, temperature, internal energy, and entropy, of course, which I am going to introduce later. And these are state functions, please remember, and they depend only on the initial and final states of the system and is independent of the path along which the system is taken. Now, as I mentioned, very many people have worked in this field, and notable among them is Sadi Carnot, who formulated the first law of thermodynamics. He is known as the father of thermodynamics, and he published his famous work in the year 1824. Now, as I mentioned, there are three important laws: the first law, the second law, and interestingly, there is another law called the zeroth law. Now, this zeroth law was invented by R.H. Fowler in 1930. Since it is a fundamental law which was invented after the first and second laws were invented, it is called the zeroth law because of its importance. Now, what does the first law tell us? The first law tells us about the definition of temperature. One second, please. The first law gives a definition for temperature. Now, the law says that every body has a property called the temperature, and this temperature is a measure of the amount of heat content present in the system. Now, before that, we come across a term in thermodynamics called the thermal equilibrium. Now, what do we mean by thermal equilibrium? If a body has different parts, and if the different parts are at the same temperature, then we say that the body is in thermal equilibrium. Similarly, if we have two bodies which are in thermal equilibrium, then they are at the same temperature. On the other hand, if two bodies which are at different temperatures are brought into contact, then it may be a direct contact or indirect contact. The heat gets transferred from the body which is at a higher temperature to the one which is at a lower temperature till the thermal equilibrium is reached. Of course, the common example all of you are familiar with. If you take a cup of coffee, hot cup of coffee, and keep it on a table, leave it for some time, the surrounding temperature is lower than the temperature of the coffee in the cup. So what happens is the hot body, namely the coffee, transfers heat to the surroundings till the surroundings and the body which is radiating, which is giving out heat, reach the same temperature, which we call as thermal equilibrium. Now, the zeroth law is very important in the sense, as I mentioned, the definition of temperature is given by this. I think there is some problem. Suddenly, yeah. Now, the zeroth law is like this. We state the zeroth law like this. Consider, for example, three bodies, A, B, and C. If A and B are each in thermal equilibrium, and they are in thermal equilibrium with another body, say C, then they are mutually in thermal equilibrium. So, for example, if A and B are two different bodies which are in thermal equilibrium, and both of them are in thermal equilibrium with C, then the property of C can be used to measure the temperature. We need not consider individually the temperatures in A and B. You take the C, which you can now call a thermometer, and introduce that in A or B to measure the temperatures. So the zeroth law of thermodynamics gives us an idea about the measurement of temperature. Existence of every body has a temperature, so there exists a temperature and it can be measured. So that is the zeroth law of thermodynamics. As you see, this is a fundamental law, and therefore even though it was invented later, it is so fundamental, it is given priority than the first law and the second law, and therefore it is called the zeroth law. Now, coming to the first law of thermodynamics, as I mentioned, the laws of thermodynamics are nothing but experience. And we all know that in any system, for example, the total energy of an isolated system, if we consider, isolated system is not interacting with the neighbors, or even if they interact, if any change takes place, the total energy is always conserved. It is possible that one form of energy may be transferred into the other form of energy, but the total energy is always the same. This is called the principle of conservation of energy. It is not law actually, it is a principle because it cannot be violated. Always this is valid. You cannot violate the principle of conservation of energy. Therefore, the first law of thermodynamics is a mere assertion of the fact that the total energy of a system is conserved. Now, to explain this, we consider, for example, a gas confined in a cylinder provided with a movable piston. And let us say we supply heat to this gas from a source. We heat this. Now heat can be added to the system or withdrawn from the system by adjusting the temperature of the source. For example, if the temperature of the source is higher and it is kept in contact with, for example, the cylinder containing the gas takes the heat, so we supply heat. On the other hand, if the temperature of the source is made lesser than the temperature of the system, that is gas, then the gas transfers heat to the source, which we later on call as sink. Therefore, by adjusting the temperature of the source of heat, it is possible either to add or withdraw heat from the system which we call as the gas. The gas is the thermodynamic system. By moving the piston upwards, let us imagine that we move the piston upwards. When the piston is moved upwards, we do certain amount of work. For example, if we supply heat to the gas absorbs heat, and in the process, the temperature of the gas increases, and also if the piston is free to move, it moves up. So there is a displacement of the position of the piston. For example, the piston moving up does some external work. That is, the gas is doing some work in pushing the piston upwards. Therefore, the supply of heat will be utilized in two ways. A part of it is utilized in increasing the temperature of the gas. Increasing the temperature of the gas means increasing the internal energy, because temperature is a measure of the internal energy, or vice versa. Internal energy is a measure of temperature. So supply of heat energy to the gas makes the gas have a higher temperature. And in addition to that, this gas does some external work if the piston is moving up, for example, if it is in a cylinder. So the quantity of heat supplied to a system is utilized in two ways. And the piston moves up, work is done by the gas. And on the other hand, if the piston is lowered, work is done on the gas. Now the quantity of heat, therefore, dQ, let us imagine the amount of heat supplied is called dQ. Let us say dQ actually is Q is the quantity of heat. dQ is already the system has some energy, some heat content. So we say dQ is the change in heat content. That is why it is denoted by dQ, a differential quantity. If dQ is the amount of heat supplied to the system, then we have this dQ as going for the internal energy du and the external work dW. Du we call as the change in internal energy, that is corresponding to that there will be a change in temperature, and dW is the external work done pushing the piston up. For example, if P is the pressure on the piston, then the work done is force multiplied by the displacement. Now force is pressure into area, because pressure is force per unit area. Therefore, force is pressure into area multiplied by the displacement of the piston, say dx. Therefore, area into dx gives the change in volume of the gas. Therefore, dW, the external work done, is PA into dx, which is PdV. dV represents now the change in volume. Hence, the first law of thermodynamics is expressed as dQ is du plus PdV. First law, as I mentioned, is the principle of conservation of energy. So, as I mentioned again, if the gas expands, work is done by the gas. And if it is compressed, if the gas is compressed, work is done on the gas. And dQ, therefore du, the change in internal energy, is dq, the amount of heat supplied, the change in heat content of the system minus the external work done. Now we have some special cases. Now before I explain the special cases, I will tell you about some changes that take place in the gas when heat is applied. When we supply heat to a system of gas, now in thermodynamics, the gas is also referred to as the working substance. And there are different types of changes that can occur when heat is supplied to a system. One of the changes is called an isothermal change. Now in this case, the pressure and volume of the gas changes, but the temperature remains constant. So if a system undergoes a change in pressure and volume without change in temperature, it is called an isothermal change. Iso means same, thermal is temperature. So changes taking place at the constant temperature is referred to as isothermal change. And there is also another change, a very interesting change, which we call as adiabatic change. Here, the pressure and volume of a gas changes, but no heat is supplied to the system nor withdrawn from the system. In other words, change in heat content is zero. du, for example, if dq, if you call, it is zero, but temperature may change in this case. So in isothermal change, temperature remains constant. In adiabatic change, heat content remains constant, but temperature may change. So in isothermal change, heat content will change, temperature remains constant. In adiabatic change, heat content remains constant, temperature may change. And so here, when the changes take place, I have got some special cases now. As I mentioned, adiabatic change, no heat content is changing, so dq is zero. Therefore, change in internal energy is equal to the external work done. du is minus dw. Minus is opposite. Then if the changes take place such that the volume remains constant, then no external work is done. dw is pdv. So dv is zero. Constant volume is there. Therefore, in such a case, the change in internal energy is equal to the amount of heat supplied. And also, if you consider a closed system, what do you mean by a closed system? A system in which there is no outward propagation or outward transmission of energy. In such a case, there is no change in internal energy. The amount of heat supplied is equal to the external work done. For free expansion, that is, this thing expands, the gas expands, no work is done, no heat is supplied. In that case, dq is zero, du is zero, dw is zero. So you have these different cases, adiabatic change and isothermal change, and during adiabatic change, heat content remains constant, temperature may change. In isothermal change, heat content will change, but temperature remains constant. So this is the important changes that take place, because when we describe the second law of thermodynamics and also one more point, when we take a gas to a series of operations, right, we can consider a gas undergoing isothermal change, adiabatic change, again isothermal change, adiabatic change, like that. And if we bring the system from some initial condition, taking it to some other condition, and again bring it back to the same original condition, it is called a cyclic process. And there are two other important processes that we have to remember in thermodynamics. One is a reversible change and the other an irreversible change. A reversible change is one in which you can bring the system back into its original condition. For example, if it is pressure is P, volume is V, and if you add heat to the system, the pressure changes to P1, V1, P2, V2, etc. But by different types of operation, if we bring back the system to the original pressure P and original volume V, it is called a cyclic process, and it is a reversible process. We come back to the original condition. On the other hand, if we cannot retrace the steps and come back to the original position, it is an irreversible process. Now, I can give you a few examples for reversible and irreversible processes. For example, if you think of for reversible process, for example, you have melting of wax. If wax melts, you can bring it back to the solid state. Then boiling water. Water boils, you can see it evaporates. You can bring back the vapor into the liquid state again. If you stretch a spring, you leave it, again it comes back. Then you fold a paper and you can take it back. So these are all reversible processes. On the other hand, if you burn fuel, wood, etc., or if there is a chemical change, or if a plant grows, or cooking food, these are all irreversible processes. You cannot bring the system back to its original condition. So, because these are two important changes that we have to remember while discussing certain other important processes that take place in thermodynamics. So, we have the various types of changes and what changes in such cases. And so in isothermal change, temperature constant, adiabatic change, heat content constant, and the pressure volume can be brought back to its origin, and also the temperature. All the three parameters can be brought back from one condition, transferring to another condition, and bringing back to the original condition is a reversible process and also called a cyclic process. You can see bring this in a cycle of order. It's called a cyclic process. Now, the second law of thermodynamics. Second law of thermodynamics is, again, as I mentioned, based on experience. We know that if a hot body is kept in a room, after some time, it radiates and the temperature of the hot body becomes the same as the temperature of the room. We call it as room temperature. That is, the heat content that is there in the hot body is transferred to the surroundings. And this transfer of heat is always taking place from a hot body to a cold body. So, heat always flows from a hot body to a cold body spontaneously. Left to itself, spontaneously, it flows from a hot body to a cold body. But there are certain cases where we have heat going from cold body to hot body. Of course, by spontaneously, this will not happen. For that, you have to spend energy. For example, refrigerator. Refrigerator is a system where you have heat going from cold body to hot body. And if you put a hot, slightly room temperature object in a refrigerator, after some time, it becomes cooler. That means heat has gone from cold body and made this hot body as cold. This is actually appears to be a violation of the common sense, but it is not, because in such case you are doing some extra spot. So the second law is important in the sense heat always flows from a hot body to a cold body spontaneously. Left to itself, a body always transfers the heat such that the hot body is becoming cold, and the surrounding cold body or the surroundings will become hot in the sense they attain the equilibrium temperature. So, in fact, it means another way of stating the second law is this. In fact, I will give you the other definitions of second law. In fact, second law is stated in different ways. It is impossible for a self-acting machine unaided by any external agency. That is very important. It is impossible for a self-acting machine unaided by any external agency to transfer heat from a cold body to a hot body. So heat always goes from hot body to cold body. And the second law of thermodynamics is actually stated in different ways. One is the Clausius statement. The other one is the Carnot statement. The Clausius statement one second, please. The other, one is the Kelvin statement. Kelvin, one second, please. See, the statement as given by Clausius for the second law of thermodynamics is like this. No process is possible whose sole result is the transfer of heat from a colder body to a hotter body. So you cannot transfer heat. Now, both these statements, in fact, the first statement which I make, it is impossible for a self-acting machine unaided by any external agency to transfer heat from a cold body to a hot body, or the Clausius statement which states that no process is possible whose sole result is the transfer of heat from a colder body to a hotter body. Both are negative statements. See, these thermodynamics, second law of thermodynamics are stated in the form of negative statements. It is impossible for a self-acting machine, or no processes, is possible. So in the sense that to prove this, we use what is called the Carnot's ideal engine. Now before that, the verification of the second law of thermodynamics is done by using what is called a Carnot's heat engine. And actually one more important parameter which I mentioned earlier, the concept of entropy, appears in the second law of thermodynamics. Now entropy has a different meaning in different cases. In fact, in statistical mechanics, it has a different meaning. But broadly, we can define entropy as the amount of randomness present in the system. And if the randomness increases, the entropy increases. And a very important consequence of the second law of thermodynamics is that in any system, if a system is undergoing changes, either reversible change or an irreversible change, entropy always changes. But the change in entropy is such that in a cyclic process or a reversible process, entropy remains constant. It will not decrease or increase. It remains constant. Whereas, if it is an irreversible process, the entropy always increases. So, entropy is a property of, like pressure, volume, etc. of a gas. Entropy is also a property which approximately defines the randomness or amount of disorder present in the system, and the entropy in a system, in a reversible system, remains constant. Reversible or cyclic system, cyclic changes remains constant, and in a irreversible process, it is always increasing. So this is a very important property of entropy, and therefore the verification, and because of this, when we transfer heat to a system and if the system does an external work, we are converting heat energy into mechanical energy, other forms of energy. And this means that when we transfer heat into other forms of energy, all the heat energy that is supplied to the system cannot be converted into useful work or useful energy. There is always a certain loss. Now, in this case, we must be careful that the loss is not due to the external changes like friction and movement of the various parts of the engine or various parts of the body like that. Now, it is assumed that no such changes in energy take place to overcome friction or to move the different parts of the body. So, Carnot actually used an engine called ideal heat engine to establish that whenever changes are taking place, whenever we convert heat energy into other forms of energy, there is always a certain loss which is not due to the external work done, like, for example, overcoming friction or moving the different parts. And it is therefore the ratio of whatever work we get to the amount of heat that is put into the system is always less than 1. And we call this ratio of the heat converted into useful work to the quantity of heat, total quantity of heat supplied to the system is always less than 1. And this particular property, this particular quantity is called the efficiency of the engine. And before I go into the details of the efficiency, etc., I will just give you a brief description of the Carnot engine. Now, as I mentioned, to establish this validity of the second law, we consider the working of Carnot engine, which is also called an ideal heat engine. It is called an ideal engine because in this engine, all processes are reversible and no energy is wasted to overcome friction or any other type of motion or loss. Now, the Carnot engine consists of different parts, 3 important parts, so to say. One is the working substance, which is a gas present in a perfectly conducting bottom and non-conducting walls and non-conducting piston. That is the first part. Second part, it also has a stand which can be perfectly insulated. And then it has a source which supplies heat to the system at a particular constant temperature, say T1. A source of heat called the reservoir is at a constant temperature T. This is the second part. And then the sink to which the heat is rejected by the engine also maintained at a constant temperature T2, let us say, and T2 is always less than T1. So the Carnot engine consists of the cylinder containing the gas which we call as the working substance, which is provided with a perfectly conducting base and a non-conducting walls and the piston. And then the source which is maintained at a constant temperature T1, normally at higher temperature, and a sink which is maintained at a lower temperature, also at a constant lower temperature. And there is a stand with has a base which is perfectly insulated. So this is in fact, you must remember the bottom of the container is conducting, and we have a stand which is perfectly non-conducting. So when we place the working substance, the cylinder containing the working substance on this non-conducting stand, no heat can enter or leave the system. That means it is useful for operating what we call as adiabatic process. Now, usually the engine is taken through a cycle of operations. There are 4 operations. First is the gas is taken under isothermal expansion. That is, it is made to expand at constant temperature. As you know, isothermal means constant temperature. So first, the gas is undergoing an isothermal expansion. And then it is made to undergo adiabatic expansion. Here, we don't supply heat or we don't remove heat from the system, but the pressure, volume, and temperature change. This is called adiabatic expansion. Then we again go to isothermal compression. The gas is compressed at a constant temperature again, maintaining at a constant temperature, and the pressure and volume change. And then we have the other operation, namely the adiabatic compression. Again, the gas is undergoing changes in temperature, pressure, and volume, but no heat is applied to the system or removed from the system. It's the adiabatic process. So if you plot a graph of these 4 changes, these 4 operations, we get a curve which is called the PV diagram. It is pressure volume graph for the Carnot engine. So as you can see, A, B, C, D is the cycle of operation. AB represents changes from the pressure P1, volume V1 initially to the pressure P2 volume V2 at the point B along a constant temperature T1, that is isothermal expansion. Gas expands from a volume V1 to a volume V2. And then from B to C, it is adiabatic expansion. The pressure changes from P2 to P3, volume changes from V2 to V3, increases from V2 to V3. But since it is adiabatic expansion, the temperature falls. Now, how do we operate this is the question now. Now, I want this to write this one. How can I? Here. I will show you here. See, for example, no. See, for example, I will show you the diagram 1 second. Take a blue, for example. Can I write? See, this is the gas, this is the stand, and you have a source, a sink. Now, when you keep this working substance gas on this, the source is supplying, this is at a constant temperature, and it is supplying heat to the system. You allow the gas to expand. As the gas expands, it takes the heat, because as the gas expands, the pressure and volume are changing. The gas is losing its internal energy, and therefore it draws heat from the source, and the temperature is maintained constant because this is completely an the conducting base. So the heat can flow, and when it expands such that the pressure becomes P2, volume becomes V2, you take out this and keep it on the stand. Here, this is completely insulated stand. Now, when you keep this on this insulated stand, then these are non-conducting sides, and this is insulating. This also becomes non-conducting. So even though this is conducting, when this is placed on this one, it becomes non-conducting, and therefore, when an operation is done, when the gas is allowed to expand further, so that the volume becomes V3 and the pressure becomes P3, this is not taking any heat or rejecting any heat, because all the sides are completely non-conducting. So in that sense, it is adiabatic expansion. So as a result of that, what happens is, because the gas is expanding and no heat is supplied, it is using this expansion at the cost of its internal energy. Therefore, the temperature falls. So make this operate till the temperature of the gas becomes T2, some constant temperature T2. And when it comes to the temperature T2, this adiabatic expansion is complete. The T2 is the temperature of the sink which we have selected. And then again you have isothermal compression. In isothermal compression, what we do is, again you bring the working substance with the cylinder, keep it on the sink, on this sink here. Sink is always maintained at a constant temperature. Now you make this gas to expand. As the gas expands, the sink actually is maintaining the constant temperature. The pressure becomes P4, volume becomes V4, and it is now undergoing at a constant temperature T2. So it is isothermal compression. You compress this. As you compress, heat of compression is generated, temperature increases. But this heat is rejected to the sink so that it is at a constant temperature. So the temperature remains constant, the volume becomes the V4, pressure becomes V4. So this is isothermal compression. And from then, again you go from D to A, that is adiabatic compression. Again bring this back, keep it on the stand so that all the sides are completely made non-conducting. And then again compress the gas. Now as the gas is compressed, this stand, this is completely insulated, therefore it will not take any heat. So no heat is supplied or given out. Therefore, what happens? Due to compression, heat of compression is liberated, temperature increases. And perform this operation till the pressure becomes P1, volume becomes V1, automatically the temperature becomes T1, the original temperature. So by this process of 4 different operations, like isothermal compression, adiabatic compression, isothermal expansion, adiabatic expansion, etc., the conducted in that cyclic order will bring the gas from its initial condition to the same condition. So this is a cycle of operation. And this system therefore comes back to the original condition. It is a complete cycle which is reversible. And what actually happens is, in each case, the gas has done some work or some work is done on the gas. For example, in the first case, that is in isothermal expansion, we have supplied heat, therefore the gas is doing work. And the work, this is the work done during isothermal expansion. And therefore I would like to tell you before that the expressions for the work done in different cases. You can show that during the isothermal expansion, the gas does amount of work because we are supplying heat. Let us say Q1 is the amount of heat supplied to the system, and therefore it is converted into work W1, and you can show that is equal to RT log V2 by V1. That is RT1 in this case, constant temperature T1, the temperature of the source, and R is the universal gas constant. Of course, sometimes people use mu RT or nRT like that. I have taken n equal to 1 in this case. RT1 log V2 by V1 to base E or base N, same base you can use. And then during the next process, that is adiabatic expansion, you are neither supplying heat nor removing. The work done by the system is R over gamma minus 1, where gamma in this case is the ratio of the specific heats. That is specific heat at constant pressure to specific heat at constant volume, Cp by Cv. That is called gamma, the ratio of the specific heats. And normally it is always greater than 1 because the specific heat at constant pressure is always greater than the specific heat at constant volume. That is Cp by Cv is greater than 1. That is called gamma anyway, that you have already studied. So work done during adiabatic expansion is R into gamma minus 1 into T1 minus T2. And then in the next process, that is isothermal compression, the work is done on the gas. So it is W3, which is, in that case, heat is removed from the system. Q2 is the amount of heat rejected by the system to the sink. That is RT2 into log V3 by V4. The volume is changing from V3 to V4. And in the next case, that is adiabatic compression, the work done is R by gamma minus 1 into T2 minus T1. Therefore, the net work done, you observe, is Q1 minus Q2 because W2 and W4, they cancel because one is positive and the other is negative. They cancel out. Therefore, the net work done is Q1 minus Q2, which is equal to RT1 log V2 minus V1 minus RT2 log V3 by V4. Therefore, the efficiency of the engine, which we define as eta, is Q1 minus Q2 by Q1. Q1 minus Q2 is the net work done. That is, heat converted. Q1 is the quantity of heat supplied. Q2 is the quantity of heat rejected to the sink. So Q1 minus Q2 is the quantity of heat which is converted into useful work or converted into energy, useful energy, divided by Q1, which is the total quantity of heat supplied to the system. That is the ratio of Q1 minus Q2 by Q1. Heat converted into useful work divided by the quantity of heat supplied to the sink is eta, which is the efficiency, and it is given by RT1 log V2 by V1 minus RT2 log V3 by V4 by RT1 log V2 by V1. And by a simple calculation using the adiabatic, in an adiabatic change, PV to the power of gamma is constant and in an isothermal change, PV is constant. Using these ideas, you can show that V1 log V1 by V2 is V3 by V4, or log V1 by V2 is log V3 by V4. And therefore, you will get the expression for the efficiency as Q1 minus Q2 by Q1, which is simply T1 minus T2 by T1. Therefore, the efficiency of the Carnot's ideal engine, remember this is ideal engine. No heat is wasted other than converting into useful work. Even in such an ideal case where there is no wastage, the efficiency cannot be equal to 1, because you can see here, eta is T1 minus T2 by T1. Eta will be equal to 1 if T2 is 0. That is, if the temperature of the sink is absolute 0. And we know that it is impossible to attain the absolute 0 of temperature. Therefore, T2 is always positive. Therefore, T1 minus T2 is always less than T1. And hence, the sink is at absolute, no, if the sink is at absolute 0, this is possible, but it is not possible in practice. Since no system can reach absolute 0, T1 minus T2 is less than T1. Therefore, the efficiency of the engine is always less than 1. This shows that heat cannot be transferred from a cold body to a hot body spontaneously. It requires an external agency, like, for example, what we do in the case of a refrigerator. So this is about the second law of thermodynamics. So to sum up, every system has a property called the temperature, which now we call as the zeroth law of thermodynamics. And then we have the first law of thermodynamics, which is the principle of conservation of energy. That is, whenever we supply heat to a system, it is utilized in two ways. Part of it is utilized in increasing the internal energy of the system, and the remaining part in doing the external work. And we also have the different processes, isothermal process, adiabatic process, etc., where isothermal process is one in which temperature of the system remains constant, but pressure and other parameters change. And in adiabatic system, adiabatic change, the heat content remains constant and all the other parameters can undergo change. And in fact, it is very interesting to note that in an adiabatic change, the entropy remains constant. In fact, sometimes adiabatic changes are also referred to as isentropic changes. That is, entropy remaining constant. Isoentropic or isentropic changes is what we call as adiabatic change. And then the second law of thermodynamics which asserts that heat always goes from a hot body to a cold body, which is a fundamental observation in nature. And this is formulated as the law by different people, Clausius, Kelvin, Planck, and others. And it is given in a as a negative statement, but it can be established in the form of the efficiency of a cyclic process. Even in an ideal situation, Carnot has shown that efficiency cannot be equal to 1 unless the sink, the other temperature of the surroundings is absolute 0, which is impossible. Therefore, no system can have an efficiency equal to 1. This is the result of the second law of thermodynamics, which also states that entropy during a reversible cycle remains constant, or entropy during a cyclic process is a constant, and entropy during an irreversible process increases. Entropy either remains constant or always increases in a system. So this is about the 2 and 3, zeroth, first and second law of thermodynamics, which I think you are sufficiently clear about the various statements and the results. So once again, I thank the organizers for providing me this opportunity, and thank you all for your patient listening. Thank you, sir. Thank you, sir. Ramesh.
Yes, sir. Sir, thank you very much for a very scholarly and informative talk on thermodynamics. Also, you spoke about different laws of thermodynamics with examples. Sure, students will be highly benefited by your talk, as most of them will be taking many competitive exams in the coming days. Hello,
Hello there.
sir, ಕೇಳಿಸ್ತಾ ಇದೆಯಾ?
ಹೇಳ್ತೀನಿ ಹೇಳಿ.
ತುಂಬಾ thanks, sir. Wonderful
Thank you.
talk. It appeared as though I am sitting in a traditional classroom. ಕೈಲಿ ಬರೆದು ಎಲ್ಲ ಅಷ್ಟೊಂದು ಕಷ್ಟಪಟ್ಟು ಮಾಡಿದ್ದೀವಿ. ತುಂಬಾ we are very grateful to you. ಸ್ಟೂಡೆಂಟ್ಸ್ಗೆ ತುಂಬಾ ಯೂಸ್ ಆಗಿದೆ ಅನ್ಕೋತೀನಿ. ತಾವು ನೋಟ್ಸ್ ಅನ್ನು ದಯಮಾಡಿ ಕಳಿಸಿ.
ಕಳಿಸ್ತೀನಿ.
Bringing out a compendium of notes for the benefit of students in the coming days. Any questions, Mr. Anthony? Anthony. Sir, law of thermodynamics biology ಹೇಗೆ ಯೂಸ್ ಆಗ್ಬೋದು?
Law of thermodynamics biological processes ಅಲ್ಲಿ it appears that the law of entropy is violating, because many systems, for example, if a tree grows,
Yes, sir.
or if a fruit tree is formed, for example, ಏನಾಗುತ್ತೆ ಅಲ್ಲಿ ಒಂಥರ ಆರ್ಡರ್ ಕಾಣುತ್ತೆ ನಮಗೆ. Tree is always growing in an order.
Yes,
So
sir.
actually ಅಲ್ಲಿ ಎಂಟ್ರಪಿ ಇನ್ಕ್ರೀಸ್ ಅಂತ ಕಾಣುತ್ತೆ. It is apparent increase, apparent violation. Thermodynamic laws, apparent violation of thermodynamic laws ಅನ್ಸುತ್ತೆ. But it is not. It is only an apparent. It appears like that, but it is not. The growing of a tree or going of a... So because ನಾವು disorder ಇಂದ order ಕಾಣ್ತಾ ಇದೆ ಅಲ್ಲಿ.
ಹೌದು.
But see, it is as if it is a apparent violation, but it is not. In practice, always the entropy increases in a irreversible way. And growing of a plant is an irreversible process. You cannot make the plant become a seed. Another seed you can get, but plant becoming a seed is not possible.
Now we have with us Dr. P. Nagaraj sir has already delivered a talk. Again, he will be delivering a talk on ATI.
Yeah, he told me, yeah.
Sir, ತಮ್ದೇನಾದ್ರು
Thank you, sir. Thank you.
for your words.
Sir,
ಹೇಳಿ.
laws of thermodynamics ಬಹಳ ಸ್ಪಷ್ಟವಾಗಿ ಹೇಳಿದ್ದಾರೆ. ಐ ಥಿಂಕ್
ಹೌದು.
ಹುಡುಗರುಗಳಿಗೆ ಅದು ರೀಚ್ ಆಗಿದೆ ಅಂತ ಅಂದ್ಕೊಳ್ತೀನಿ. ಯಾಕೆ ಅಂದ್ರೆ ಐಸೋಥರ್ಮಲ್ ಚೇಂಜ್, ಐಸೋಬಾರಿಕ್ ಚೇಂಜ್ ಅನ್ನೋದೊಂದು ಮಿಸ್ ಆಯ್ತು ಅಂತ ನನಗೆ ಕಾಣಿಸುತ್ತೆ, ಅಥವಾ ನಾನು ಕೇಳಿಸ್ಕೊಂಡಿಲ್ವೋ ಏನೋ.
ಅಲ್ಲಿ ಇಲ್ಲಿ ನಾವು ಯೂಸ್ ಮಾಡಿಲ್ಲ ಅದನ್ನ.
ಆಗ್ಲೇ ಹೇಳಿದ್ರು ಐಸೋಥರ್ಮಲ್ ಚೇಂಜ್, ಅಡಿಯಾಬ್ಯಾಟಿಕ್ ಚೇಂಜ್ ಅಂತ. ಯಾಕೆಂದ್ರೆ ಅಡಿಯಾಬ್ಯಾಟಿಕ್ ಚೇಂಜ್ ಅಲ್ಲಿ ಹೀಟ್ ಕಂಟೆಂಟ್ ರಿಮೇನ್ ದ ಸೇಮ್ ಅನ್ನೋ ಮಟ್ಟಿಗೆ ಹೇಳಿದ್ರು. ಅಂದ್ರೆ ನಾನು ಅಂದ್ಕೊಳ್ಳೋದು ಏನು ಅಂದ್ರೆ ಐಸೋಥರ್ಮಲ್ ಚೇಂಜ್ ಕಾನ್ಸ್ಟೆಂಟ್ ಟೆಂಪರೇಚರ್ ಅಂಡ್ ಅಡಿಯಾಬ್ಯಾಟಿಕ್ ಚೇಂಜ್ ಅಂದ್ರೆ ಥರ್ಮಲ್ ಐಸೋಲೇಷನ್ ಅನ್ನೋ ಒಂದು ಇತ್ತೇನೋ ಅಂತ ಅನಿಸ್ತು. ಇಷ್ಟಿಟ್ರೆ ಹುಡುಗರಿಗೆ ಏನ್ ಬೇಕಾಗಿತ್ತು ಅದೆಲ್ಲನೂ ಚೆನ್ನಾಗಿ ರೀಚ್ ಆಗಿದೆ ಅಂತ ಖಂಡಿತವಾಗಿ ಹೇಳ್ಬೋದು ಸರ್. ಸೊ ಥ್ಯಾಂಕ್ ಯು. I think
simple language
will be definitely benefited by his talk. Thank you, sir.
ಹೌದು. ಬಹಳ ಸಿಂಪಲ್ ಲ್ಯಾಂಗ್ವೇಜ್ ಅಲ್ಲಿ ಡೀಟೇಲ್ ಆಗಿ ಈ ಟ್ರೆಡಿಷನಲ್ ಕ್ಲಾಸ್ ರೂಮ್ ನಲ್ಲಿ ಬರೆದು ಹೇಳ್ತಾರಲ್ಲ ಆ ತರ ಸರ್ ಎಕ್ಸ್ಪ್ಲೈನ್ ಮಾಡಿದ್ರು. ತುಂಬಾ ಯೂಸ್ ಆಗುತ್ತೆ ಸರ್. ಕ್ವೆಶನ್ಸ್ ಹುಡುಗರು ಯಾಕೋ ಲಿಟ್ಲ್ ಬಿಟ್ ಶೈ, ಹೇಳಿ ಅಂತ ಹೇಳಿದ್ರು ಕೇಳಿಲ್ಲ. ಮುಂದೆ ಏನಾದ್ರು ಡೌಟ್ ಬಂದ್ರೆ ಇಮೇಲ್ ಕಳ್ಸಕ್ ಕೇಳ್ತಾ ಇದ್ದೀವಿ. ಅದನ್ನ ನಿಮ್ಗೆ ಫಾರ್ವರ್ಡ್ ಮಾಡ್ತೀವಿ, ತಾವು ಆನ್ಸರ್ ಮಾಡಿ.
Okay.
We are very grateful to you for your very informative and scholarly talk. Thank you, sir.
Thank you.
Thank you, sir.
Thank you very much. I also thank all the participants who joined for this very informative talk. Tomorrow again there will be a talk at 4 o'clock. All of you kindly join. Sure, you are going to be benefited by these expert talks, both in your coming competitive exams as well as beyond. Means when you join your degree courses, these talks will be of use, and you can watch these talks on YouTube also. Whenever you find time and you want to visit these talks again, you go to KSTA YouTube channel and can watch again, and be sure that you get good message for your exam. Thank you very much. Take care.